Hi, we're Group 4, and our project was to optimize the design of a composite lower spar cap. Our group members are Garrett, Cashwell, Andrew Fluevog, Caroline Jones, and Jonathan McKown.
Our objective was to design a composite spar cap, shown in the bottom left figure, and it'll be modeled as a 5x12 rectangular plate with an unknown thickness. And this spar cap has to withstand the given loading of a moment in the x direction and tensile loads in the x and y direction. The loading is shown in the bottom right figure. Our fixed design variable as Team 4 was that we had to use an epoxy matrix, and our variables that we could change were the type of fiber that was able to be used, the fiber volume fraction, the laminate type, and the angle of each ply. And our goal was to optimize the thickness, cost, and weight. Throughout this presentation, we will talk about how we thought about the trade-offs between trying to get an optimal strength out of the composite part while also minimizing thickness, cost, and weight. So for our initial conditions, we chose a TG-DDM epoxy matrix. The reason for this was there was a lot of industry field testing and it had the most mechanical data available. For the fiber type, we chose IM7 carbon fibers. We chose carbon fibers in general due to natural fibers being low strength and having high discontinuities. We did not choose boron or glass fibers due to their high weight because they have high compressive strengths. However, because we do not have any compressive forces, we did not need that. And we chose carbon fibers over aramid fibers. Even though aramid fibers offered slightly higher strengths, their costs were exponentially more, so we decided to go with carbon fibers. As for IM7, we chose this because this was the most used carbon fiber in the aerospace industry, as well as having ample amount of testing. For the lamina type, we chose unidirectional continuous. This is because they are the strongest type of lamina, as opposed to unidirectional discontinuous and random. For thickness, we wanted to consider that the thinner the lamina, the more in plane the stresses were, and this was one of our assumptions. Therefore, we tried to go as thin as we could without having to require too many plies. So therefore, we chose a standard thickness of 2 millimeters based off of prepregs available. For the stacking sequence, due to there not being any shear forces applied, we decided to only use plies in the 0 and 90 degree directions. And for our volume fraction, we started with 0.6 because this was what was commonly seen in the textbook and in the examples that we did in class.
For our analysis, we used the laminator software shown in the bottom left figure. By inputting our ply orientation and given loads, the software calculated the stresses and strains in the midplane of each lamina. For our failure criteria, we used the first ply failure method for both maximum stress and strain. This meant that at any time a single lamina had a stress or strain over the failure value, the entire laminate was considered to have failed. This is a very conservative method, but allows for us to have an extra safety factor automatically designed in, which is beneficial for aerospace use. An example of this analysis is shown on the right. The laminator software takes the stress and strain in each lamina and divides it by the max value. The numbers are then outputted as shown. If any value is below 1, that ply has failed, and therefore the entire laminate failed. As seen, the minimum value for stress and strain for this case is 1.08 and 1.22, so the laminate has passed. When analyzing the stresses and strains of our initial laminate, it became apparent that each lamina was much closer to failing in the transverse direction than the longitudinal. In addition, the longitudinal loading on the laminas was less than half of their failure strength. To fix this issue, the team investigated the effect of changing the volume fraction of our laminas. The graph on the left shows the effect of changing the fiber volume fraction from 0.3 to 0.6 on the tensile strengths of each lamina. As shown, the longitudinal tensile strength increases as the fiber volume fraction increases, while the transverse tensile strength decreases. Therefore, it was beneficial to decrease the volume fraction. For the exact value, the figure on the right shows a plot of the safety factor as a function of the fiber volume fraction. A higher safety factor corresponds to a laminate with higher strength. Therefore, a safety factor is a value that the team wanted to optimize, so fewer plies would be needed, resulting in overall lower thickness. A value of 0.35 for the fiber volume fraction gave the optimal safety factor, peaking at 1.56, and was therefore chosen as the value for VF.
After optimizing the fiber volume fraction, we began working on the progression of our ply orientation. First, we began with only 0 and 90 degree plies. However, even though we did not have shear forces, we found that it was beneficial to have 45, 60, and negative 60 degree plies included. We later started altering angles as we saw certain plies failing to help spread out the loading, and eventually we were able to remove multiple plies. This led us going from 60 plies in our first orientation to only 39 in the final. For our final design, we found the estimated costs from CES EduPack. The IM7 carbon fibers cost $56.55 per kilogram, and the epoxy matrix cost $3 per kilogram. Using our final orientation with a 0.35 volume fraction and 2 millimeter thick unidirectional continuous laminas, we found our cost to have decreased from $287.51 to $113.73.
In conclusion, given the loads for our composite spar cap, we discussed the epoxy used, the fiber type, the lamina type, the thickness, the stacking sequence, and we discovered that the volume fraction was the overall design driver. We used the laminator for all of our analysis and given outputs, and we were able to come up with a 35% decrease in thickness, a 40% decrease in weight, which led to an overall 60% decrease in cost. Thanks for listening to Group 4's presentation. We would like to note that although only 2 group members spoke, all 4 group members contributed evenly to this presentation. Thanks.